Good day, this is Jim Pytel from Columbia Gorge Community College for Renewable Energy Technology. This is RIT 120 Hydraulics. Today we're going to have a discussion about one of my favorite topics, regenerative extension. And again, when an instructor says, hey, this is my favorite topic, what's going to be on the test? So before we do this, though, I want to talk a little bit more about our manifolds. As much as the advantages are for manifolds, I mentioned this earlier, you basically your manifolds, an aluminum block through which the standard configurations of pressure and tank ports, is compact and free of potential leaks associated with external plumbing, so here's a directional control valve. It's put on top of that thing, as opposed to like an inline, here's a directional control valve or a valve, whatever it is, it's inline. All your connections are here. There's a disadvantage to these things. Number one is the manifold themselves. They're dirty. Do me a favor, do you a favor, and do your boss a favor, your future boss a favor. When you get a new manifold, clean this thing because these things are milled out. And inside these passageways, they're quite commonly filled with shavings, which would absolutely wreak havoc on a hydraulic system because it depends upon those incredibly tight tolerances between our lands and our passageways and our spool. If particles get stuck in there, that valve spool is going to stick. Tiny particles are going to wear things away and you're going to start developing a leak between there. Okay, so that's enough about manifolds there. Just clean them out when you get them out of the box. Let's go on to my favorite subject, regenerative extension. The reason why this is one of my favorite subjects, it is just so cool because you almost get something for nothing. This is like one of those moments where you're using a screwdriver on a screw and right next to you, you see a nail that needs to get hammered. All you do is take the business end here, make the business end here, and you got a hammer. So that's what regenerative extension is you're using the same components, but you're getting something more out of the same components. So let's just do a simple schematic here. And here's our simple schematic that we're going to talk about. And this is what was actually brought to me. This is a true story. A farmer brought to me a log splitter that was hooked up in the following fashion. And he says, Jim, I don't understand why this log splitter is going so slow. And this is the deal. These cylinders, as comically big as I've drawn them in the schematic, are huge. They're 3-inch diameter, 24 inches long. And there's 2 of them hooked in a parallel fashion. And they've got the rods that come out here, and they're hooked together with a mechanical yoke with a splitter right here. And a mechanical yoke is quite often used to make sure that each cylinder is sharing the same load in a parallel combination. And what we know from a parallel combination, a cylinder with the least load requirement, least pressure requirement will extend first. So basically what the mechanical yoke here, like an oxen, you're yoking the 2 cylinders together. And obviously this is the splitter, that's the business end of that. It's making sure that each cylinder is equally loaded and they will extend simultaneously. And it was the funniest thing when this farmer brought it to me. He says, I don't understand why it's extending so slowly. I've got a pump that produces 1 gallon per minute. And I instantly started laughing. Think about how much it takes to fill 1 cylinder, one of these big boys. Now imagine filling 2 of them at a flow rate of 1 gallon per minute. I mean, just do the math here. The cap end of these things has an area of pi over 4 d squared, where d is 3 inches, 7.069 inches squared. The volume of a cylinder, that's 7.069 up here, that's 24 inches long. It's 169.6 cubic inches, which is 0.734 gallons. But now keep in mind, you're filling 2 of those things. Your total volume, 1.468 gallons at a flow rate of 1 gallon per minute. 1 gallon, 60 seconds. How long does that take to fill up? Yeah, it's 2 of them. 88 seconds to split a piece of wood. It's a minute and a half to split a piece of wood. And I said, my farmer friend, I can save you a lot of time. And that's what I taught. That's why I really, really like regenerative extension. It's using the same stuff, but using it in a different fashion to save yourself time. Okay? So regenerative extension is commonly used in industrial practices where it's a repetitive motion, or if it's a motion that requires quick action. Okay? And here's how you do it. And let's go into a caveat here. What would happen? And you've already done this in lab. If I put pressure to both sides of a cylinder, both the rod end and cap end, and your immediate incorrect answer is that it does nothing. And this is the reason why that is incorrect. Pressure is equal on both sides, but area is not. And the force imbalance that occurs is because there are an imbalance of areas on either side. Cap end looks like this. Rod end looks like that because you've got to remove active area where the rod is. Okay, so same pressure, bigger area. Who wins out? Well, the force developed by the cap side wins out and the cylinder extends. Okay, so this is how regenerative extension works. What is happening to the flow in the cap end? Excuse me, in the rod end. Well, it's coming out and going back into the cap end. Pressure is the same, flow is simply rerouted in there. What's the difference between the volume of the cap end at full extension and the volume of the rod end at full extension? Obviously, the only thing that's missing is the rod. So if you've got this right here, and you've already got that, basically here, let's do that again. You want to fill up this, and you've already got this. What do you need? That guy. So at a flow rate of 1 gallon per minute, how long does it take to fill up that incredibly small space? Incredibly quickly, okay? And that's how a regenerative extension works. So let's talk about some of our positions. We've seen something like this, and that's a float center position. There's another position that looks the same, kind of, but it's totally different. P, T, A, B. That's our regen position. Whereas a float has A and B hooked up to T and P is closed. Regeneration has P hooked to A and B and T is closed. Okay? Pressure to A and B. And because of this phenomenon, which I just talked about here, where there's an area imbalance, that cylinder will continue to extend. And because of this phenomenon here, where the rod end volume is being shoved back into the cap end here, all we have to come up with is that. So let's look at that same log splitting example, which is probably still in the front of Valley Hall right now, or the side. Let's see how fast we can make this thing extend in regenerative extension. Okay, so let's start with our calculations. At full retraction, what's the volume of our rod end? Well, first off, we're going to figure what is the surface area of our particular rod face. Let's pretend they've got a rod, it's a 1-inch diameter. So area of the rod, pi over 4, d squared, 0.7854 cubic inches. Whoops, inches squared, excuse me. So area of the rod face is equal to the area of the cap face, 7.069 minus 0.7854 should give us a volume, an area of 6.823 inches squared. And again, we can already see that there is an area imbalance. The area of the rod face is smaller at 6.283 inches squared than the area of the cap face at 7.069 inches squared. Because F equals P times A, this guy is the same, but this one's different. Dig? Because there's an imbalance that occurs, and that rod will still extend when pressure is on the same on both sides. Okay, but now what's the volume? Again, so the volume of the rod end is now equal to an area of 6.283 times 24 inches, because again, at full retraction, it's fully retracted at 24 inches, should give us a volume of 150.8 cubic inches, which is a volume of 652 gallons. Okay, so full extension, we need to fill up a space, as we determined earlier, 0.734 gallons. But by the act of filling up this space, we are taking, because remember we're hooked up in this fashion, P, A, B, from the rod, which was at full retraction. We're taking that volume of 0.652 gallons and shoving it back in here. What is the amount of flow that we need to make up? Well, quite obviously, the rod, the volume of the rod itself. Okay, so if you do the math, 0.734 minus 0.652, roughly 0.082 gallons. And confirm, just to make sure you're absolutely doing this correctly, what is the volume of the rod? Well, we could also do, here actually, let's do it this way. What is the volume of the rod? Well, if the rod was an inch squared, I just discovered something wrong here. That's the cap. Oh, the volume of the rod, yep. No, I did that. So if the area of the rod was 0.784, so area rod times the height of the rod, 0.784 times 24, 18.8 cubic inches. Is it in fact equal to 0.082 gallons? Yes, it is. Divided by 231 cubic inches, you get 0.082 gallons. So now, what is the resultant extension time for our particular system of the big guns hooked in a regenerative extension mode? moves, or pressure is applied to both of those. Again, we're fully retracted, got a volume of, as we determined, 0.652 gallons in each one. And as that pressurized flow enters here, it's equalizing pressure, but it's pushing this way because of the area imbalance. And that flow re-enters from the rod end, re-enters the cap end. And we're trying to fill up a space of 0.734 gallons in each one, so 1.468 gallons. We've already got minus 0.652, minus another 0.652. What is the required volume that we need to fill up? Well, and shortcut all that, it's 2 times 0.082. Which is 0.164-ish. I know there's some rounding errors here. So 0.164 gallons. How long does it take to fill up 0.164 gallons when you're at a flow rate of 1 gallon per minute? 9.8 seconds with a huge exclamation point. 9.8 seconds to extend those rods hooked in a parallel fashion on those two cylinders versus 88 seconds. Now again, in a log splitting operation, you have saved yourself a lot of time because that's a single stroke. You went from 88 seconds down to 10 seconds roughly. So you've saved 78 seconds on a single stroke. And as we all know that there is a lot of logs and a cord or 2 cords or 3 cords of wood. Think of how many times you're saving 78 seconds. That is a lot of time sitting around a campfire that you've saved, okay? So this is illustrative of something very important, a repetitive industrial process. You're doing this thing over and over again. You've saved all that time on a single action, but now repeat that action over and over. You could save hours in production time doing this. And now some of you may be thinking, this is too good to be true. Why isn't everyone doing it this way? And the answer is, it is too good to be true. This is obviously an idealized means where the volume of the rod end is instantly shoved into the cap end. So there is some incorrection, some difference between our theoretical calculated values and what we obtain. But the other problem that is occurring here is substantially faster, no doubt about that. But think about the force. There is a trade-off. There is a trade-off that is occurring in regenerative extension. Here is the cap end area, which, as we determined before, 7.069 inches squared. And it's equal pressure on both sides. The rod end has an area of 6.283 inches squared. And again, equal pressure on both sides. Let's pretend it's 800 psi. 800 psi. Pressure is equal, area is different. So obviously it extends because this area is bigger than this area. But still, this annular area, pressure is applied to that, and it is pushing a force back. It's the force imbalance that makes it. Yes, I know the force here is greater than this force, but they are still in opposition to each other. So force will be substantially reduced. There's 2 ways of doing this. Calculate the force of the cap. subtract force of the rod end, or what's the imbalance area? The only imbalance exists is the cap end pushing that way, because again, cap minus the donut, what do you get? The donut hole, okay? So there's two ways of doing it. You're going to get the same answer. So force of the cap, again, 800 psi times an area 7.069 inches squared, 5,654 pounds of force. Force on the rod end, again, pressure times area. The area is smaller. You get a force of 5,026 pounds. This one is greater, but this one's opposing. What's the difference between them? The answer, 628 pounds of extension force. So here's a shortcut. What's the force, the pressure of 800 times the area in balance? What is the area of the rod? .7854 inches squared. So 800 times 0.7854 inches squared. Surprisingly enough, 628 pounds. So our potential force, if we were capable of just doing this right here, where instead of hooking this in regenerative fashion, we P2T, we could potentially produce 5,654 pounds of force. Each cylinder could produce that force, 800 psi at 800 psi. But because we're in regenerative fashion, yes, it's extending substantially faster, but we can only generate 628 pounds of force. So there is a trade-off for speed. You reduce the amount of pressure. Now, you might be thinking, you're like, well, what happens if I got a log in there that requires 628 pounds, more than 628 pounds of force? Well, it's quite obviously to your advantage to go to this method. But again, it's that time that you want to save. So you often see these things working in combination. Basically, where to extend the cylinder to the distance that you need to travel when it's going against free space, air. Here's our splitter, here's our rod. We lay a log here. Be in regen mode right here. You're in this mode right now. Extending that cylinder as rapidly as possible at the weakest force possible, because there's nothing in opposition here. You don't need a lot of force to cut through clean air. What you want to do is get it there as fast as possible. And then as soon as you make contact with that log, you can either have a pressure sensor or hire your brother to go ahead and switch it over to our straight through condition, basically another position within that same directional control valve. And now you're extending slower because you're not in a regenerative extension mode, but you're extending at an incredibly strong force. So here's slow and strong in this travel. Here's fast and weak for that particular application. This is not just limited to industrial practices like getting something fast across a distance of no pressure. and then going slow and strong. This could also, and this is, you're going to commonly see this thing. Here is inside a hub of a wind turbine. There's a cylinder on a trunnion mount. I know we haven't discussed these mounting things, but basically as this cylinder extends, it's going to drive that wheel, almost like a locomotive. You understand what I'm saying? It's going to spin that wheel in that direction. And what would happen if the cylinder at the initial portion, you know, and what is this doing? What is this doing, by the way? This is inside a blade. You know, it's pitching a blade, turning it this direction. That's full power if the wind is coming from this direction. That's full power, and you want to pitch it out of the wind, basically cut through the wind. That's the wind right there. You want to, it's basically an emergency procedure to stop a wind turbine blade. You got to pitch it one way or the other. So again, it's locked in this full power position, and obviously it's going to be the hardest to move because of static friction because the object is sitting there. So why not, for the first portion of this cycle, put it in a mode where the cylinder is getting P and T at a full force mode. But once it's rolling, once that blade has started to pitch, you don't need that much force to keep it going. You know, rolling friction is substantially less than static friction. Why not put your cylinder in a regenerative mode where it's weaker force, but that cap flow is coming back, excuse me, the rod flow is coming back to fill up the cap end, supplementing it. Yes, we've lost the force, but we're greatly making up for it in speed. Again, a pitching operation, speed is the name of the game. Let's say you've recognized an emergency condition, you need to go ahead and pitch that thing as fast as possible to a no power position. So all you got to do is break that static friction with incredible force and then instantly go into regen mode. And by the way, a valve is not the only way of doing this. You can use some pilot to close check valves, various use of manifolds, which we'll be doing in lab to create a regenerative extension mode. Again, what's the advantages of a regenerative extension? Incredibly fast. What's the disadvantages? Incredibly weak because of the area imbalance. What's a smart way to use these things? Use them in combination. When you need to go fast and weak, be in regenerative. When you need to go slow and strong, go regular traditional P to T on the cap and rod end of a cylinder. The other thing too is just think of a real world example like this log splitter here. I know that I said that's a 24-inch travel. You expect a 24-inch, you would expect to be okay, and I can be in regenerative mode for 24 inches. Well, that's absolutely false. You can be in regenerative mode. Let's pretend this is a 16-inch log. You can be in regenerative mode for 8 inches because once you hit this log at 16 inches, you need to go slow and strong. And I know some of you guys are saying, well, yeah, once you split the log, you can go back into regen. Yes, you can. As long as you pay your brother enough to operate that directional control valve while you're chucking them logs, yes, you can do that. Do it that way. But again, your theoretical extension, using all our funky math up here, you're never going to get that 9.8 seconds. And you're not going to be saving 78 seconds each stroke there. But be aware that this is the way to save yourself substantial amounts of time with regenerative extension.